So worksheets, Bochy's divider bias. And then circuit number 1. Of course, all I'm going to do is just clip the circuit out and copy it over to Blackboard. Over to PowerPoint. Didn't copy. Okay, here's circuit. Okay, so all of them solves the same. So first thing we're going to do is solve for VB, which would be VR2. Oh, wrong thing, sorry. So VR2, which is equal to VB, is going to be equal to 10K over 50K, or 10 over 50, or 1/5, right? You'll see a lot of this. Then we're going to multiply this times 10. So what have we got? Circuit. You had 40K, 10K, 2K, and 6K. They divide that by number 2 resistor times 10. That's not how it's done. No, I don't. I can't even follow what you're saying. This is we call this the voltage divider formula. So in a series circuit, every resistor drops a voltage that's proportional, that's determined by the other resistors in the circuit. It's a ratio of resistors. So any series circuits, you could solve for the voltage drop without even solving for I. And what's nice about doing that, and we happen to, so I could get into DC and I can say, okay, I've got this series circuit and it's got 10 volts applied to it, and everybody would solve it. And I say, what happens if we raise the voltage to 20 volts? And everybody would solve the whole circuit again, even though this resistor right here will always drop 1/5 of whatever voltage you have applied to this circuit. So the voltage divider formula is the formula that we use most often up here, because we don't have to. So if you solve for I, you got to solve for R. You got to solve for RT anyway, right? You understand that? But here, what we're doing is we're saving one whole formula, and every little step that you take, every formula that you put in there, the other chance you've got of making a mistake. So we call this the voltage divider formula. The voltage divider formula says VRX, whichever resistor you want to solve in a series circuit. Now, it don't work in a parallel circuit because voltage is constant. Is equal to the value of RX over RT. And that gives you the ratio of that resistor to all the resistors in the circuit. And then you multiply that times your voltage source. Of course, here our voltage source is what we call VCC. And this is called the voltage divider formula. The current divider formula in parallel would be IRX would be equal, and everything swaps around, IT over IX. No, I'm sorry. I'm giving it to you wrong. Don't pay attention to it. It would be, it's going to be RT over RX times IT. And this is the current divider formula for parallel. So notice everything switches around, because current
and opposition are inversely proportional. And inversely means you just swap it around. So this is two formulas that you should have played around with a little bit in DC. Huh? Oh, okay. It is the right answer, but I put 12. Okay, thank you. So it is 10. It's just when I put the formula that I have to show y'all one day what it's like to put formulas in there. It's not easy. And no, it don't do the math for you. So it's just that I keyed it in.
I remember, so the first thing you go, we try to solve PD, right? So you still.
What do you mean VD? There's no such thing as VD. Okay, we're going to solve for V. What we're trying to do is we're solving for VR2 first.
And you took the 10K and 40K, add both of them, divided by 10. Divided by 10, 10 divided by 10.
No. You might be saying it right in your mind, but you're not saying it where I can understand it. We take R. What R are we trying to solve for? We're trying to solve for R2. We divide that by RT. RT is 40 plus 10, 40 plus 40K plus 10K is 50K. So we're taking the value of R, dividing it by RT. Okay. And then that gives us the ratio of that resistor to the rest of the resistors in the circuit. And then we can multiply that by any voltage and it'll come up that's applied to the circuit and it'll give us the voltage drop across that resistor. So that makes sense, Charles? Okay. But what we can do is what I can do right off the bat, which makes my math easy, is I can come up here and I know it's got K on the top and the K on the bottom, so what would it do? It'd cross that. I got a 0 there and a 0 there, what would it do? So that means that resistor is going to drop 1/5 of the voltage. Period. Then I can take that, once I get the fraction, I can multiply that by 10, and then I can come up and get the voltage that it would drop. So what voltage would it drop? It's going to drop 2 volts. By George, I could have done that one in my head, just because of the ratio of the resistors. Then I need VR1. Well, VR1 would be equal to what? 10 minus 2. So VR1 is going to be equal to 8 volts. That's Kirchhoff's voltage law that says all the voltage in the series circuit have to equal to the applied voltage. So we know the voltage drop across R1. We know the voltage across R2, right? You understand that? Everybody okay there? And we know the and it's only 2 resistors. Then I can solve for VR4. VR4 is real hard. It's going to be equal to 2. The voltage across R2, which is equal to 2 volts, minus the drop of our P-in junction, which is 0.7. So VR4 is going to be equal to what? 1.3 volts. Now I can solve for the current flow through R4. So IR4, which is equal to IE, which we assume is equal to IC. We know they're not, but we know it's so dang close that we're going to use it anyway, right? You understand that? Well, this is going to be equal to 1.3 divided by 2K. What's that going to give you? There's a point in there that didn't show up, guys. What's that? Okay, 650 microamps. Well, we're okay now. So now I'm working on this series circuit over here. So here's my series circuit over here. This is the direction of my current flow. So if I've got 650 microamps flowing through that guy right there, I got 650 microamps flowing through my transistor, and I got 650 microamps flowing through R3. So what can I solve for? Well, I can come up here and I can say, well, let me get my black pen back up. I can say VR3 is going to be equal to 6K times 650 micro. Huh? It's Ohm's law. V is equal to I times R. If you divide, there's no such form as resistance over current, right? I don't know what you decide. You okay? Yeah, this, what laws are we using so far? I mean, where'd you learn this at? DC. In fact, this is a lot easier. Allison's over there teaching series parallel circuits over there, and that's what this is, a series parallel circuit. But it's one of those things, you know, where it's a voltage divider where you come up here and you have this one and this one and this one, and you come over here and branch off that one, and then you branch off this one, and then you branch off this one, and solve for that circuit. And that's one of the circuits they're solving for DC. This is one of the circuits y'all had in DC. And this is, what we're doing here is what? I mean, I wish this was the circuit that, I mean, when I took DC, the guy drew them like this. He'd draw them in triangles like this, and then he'd go over here and do like this, and then he would go over here and do another triangle. That's the parallel circuits I got into. When I got into these transistors, I was like, hey, yeah, you know. So what would be the voltage drop across R3? Huh? 3.9 volt? So now I can solve for VC. VC is going to be equal to 10 volts minus 3.9 volts. Y'all understand that? Because VC is measured right there. And what is that? Well, that's after the voltage drop of R3. So what does this give us? 6.1 volts. So we're operating toward cutoff. Then I can calculate VCE. VCE is very, very important because this tells us the region that the transistor is operating in between. So I'm going to take what's on my collector. So what's on my collector? 6.1. What's on my emitter? My emitter is 1.3 volts. And this gives me my voltage collector to emitter. I'm listening. Huh? Well, it's going to be 8. Yeah, 4.8. What else do we need to solve for? What else is the worksheet? Huh? VE, we solve for VE way up here. We solve for VB way up there. VR2 is VB. Because VB is, here's where we measure VB. Well, VB is across R2. What else is it we need to solve for? So VB is 2 volts. VC is 6.1 volts. Of course, VE is so VE, so I said VR4, this is, I didn't put that up there. So VE is VR4. Here's VE right here. That's what I measured, VE. That's VE. So we give these different measurements names, you know, we call them VE, VC, but all it is voltage drop across a resistor or voltage across, and what you have to do is just picture in your head where these measurements are made. This is the one that gives people problems right there, VC. They want to use that for VC. That is not VC. VC is not measured across that resistor. VC is measured at the collector to common. So the only difference between VCC and VC is the voltage drop across it in this situation right here, R3. What else do we need to solve for? AV in this situation is going to be equal to 6K over 3K, so this is going to have a gain of 2. It's a very poor amplifier, but you got to understand these worksheets are not intended to be good amplifiers. They're just in here to get us to learn how to do the math. Now, if I was to come up here and put a load out here, let's go ahead and look at that too while we're here. This is unloaded. So what would you expect to happen to the gain if I come up here and put a, we'll make it real easy. I put a 6K resistor out there. What would you expect to happen to the gain? Would the gain go up or would the gain go down? And we're not going to have an amplifier if we don't load it. I mean, it'd be stupid for me to have an amplifier that I don't hook a speaker up to or something up to, right? You understand? So what I just did is I loaded this amplifier with 6K. Now, it can be anything. It could be another amplifier stage. It could be something out there, but it's going to represent an R value, right? You understand that? So what would we expect to happen? Would we expect that gain to go up or would we expect the gain to go down? So I've got a battery, and I measure that battery unloaded with my meter. And then I come over here and I put a resistor across that battery. What would you expect the voltage on that battery to do? Would the voltage on that battery go up or would the voltage on the battery go down? If you've got your meter out there on your car and you're looking at it and you hit that starter on that car, does the voltage on the battery go down or does it go up? It does. That would be great. That would say that the battery has absolutely no internal resistance at all. And there is no such thing as a source that has no internal resistance. Now, in regulated power supplies, we compensate for it. So what we do is that if the load goes up, we put more energy into it. That's what the regulator does. If I didn't do that, if I load a source, it goes down. So if I load this amplifier, the gain has got to go down. We can't get more out of it when it's loaded. And that's why I say that would be great. I go out there and get more voltage out of my battery when I'm trying to start the dang thing. Go out there and don't run your car because you got a regulator when your car's running, right? You understand? That pumps more energy into the alternator if you try to load it down. But go out there and get your meter one day and just put it on your car and turn the headlights on. What do you think that battery's going to do? What's the output voltage on the battery going to do? Is it going to go up or is it going to go down? It's going to go down. So when I load this amplifier, this gain is going to go down. So that gain of 2 is unloaded. So how would we do this? Well, we're going to do the same thing, except we're going to look at this as a parallel circuit. Here's where the output is generated, right there at that collector right there. So if I follow this out, I have 2 paths I can go. I can go through the 6K up and I can go through the 6K out. So what we would do is we'd say, okay, that means instead of having 6K, I would have 3K. So now my AV would be equal to 3K over 3K, and I just lost my amplifier. Because my gain now would be what? Would be 1. So that's what we do when we load it. So the formula is R out. It's not R. It's not RC. It's R out. And this is what you're going to run into because you will never build an amplifier unless you do what? If you load it. So I've got a ton of batteries in there, and they're not doing any good because they're not powering anything. It's when those batteries do work, where you get, the use of a battery. In fact, I threw one away today. I went in there and it's been in the box so long it corroded and ate itself up. So, but all of them are solved exactly the same. These are all unloaded. What's the function? What do we call this capacitor right here? What do we call these 2 capacitors right here? What do we call these coupling capacitors? Because what they do is they let the AC cut. So over here we have AC. Over here we have DC. We got 2 volts sitting up there. What does a DC voltage see an AC source as? Let's see if we can demonstrate this on the electronic workbench. So what does a DC source see in a? So if I was to come over here and put a DC battery across an AC source, what would it see, what would both of them see each other as?